Hello, in this lecture I am going to discuss the Blasius solution for flat plate boundary layer. The boundary layer equations for the flat plate are dou u by dou x plus dou v by dou y is equal to 0, u dou u by dou x plus v dou u by dou y is equal to u into dou squared u by dou y squared. So these are the two equations to be solved for the unknowns u and v. And as far as flat plate bond layer is concerned, we have the edge of the bond layer something like this. Edge of the bond layer, the velocity variation at different axes can be plotted like this. So, it is like this. So the flat plate is facing a uniform flow with velocity u infinity, edge of the bound layer is also u infinity, velocity is u infinity, velocity is u infinity, and this is x, and this is normal to the flat plate, normal to the flat plate. So these are the bound layer at different x's, x1, x2, x3. And if we are plotting this velocity along some plot like this along y direction, along the y direction, if we are plotting x direction, we are plotting u, then the velocity variation at different x's will be, the first x1 will be something like this. And this is for the x1, this is for the x1, and next for the x2, the velocity variation will be something like this. So at larger values of y, this curve asymptotically goes to u infinity. That is the edge of the bound layer. So maybe the bound layer, edge of bound layer will be different. So this curve will be getting the edge of the bound layer at early. So x3 will be something like this, like that. So this is x1, this is x2, the second one is can be x2, and this is for the x3. For increase of x, it is like this. So the basis for the solution of Blasius flat plate bound layer is on the assumptions that these curves at different x's will converge or collapses into a single curve if it is plotted. The variation is plotted on a different y-axis. So that on a normalized y-axis, normalized by the bound layer thickness. So we have at different delta 1, delta 2, delta 3. So that is also increasing with the x. So if we plot on the along the x-axis some u velocity, and on the y-axis if we are uh, taking the y, if we are taking the on the y-axis we are taking the y by delta, that is a dimensionless variable. Y is vertical distance, delta is also a distance along the normal direction to the flat plate surface. So this along the x-axis, this is u by u infinity, that is also a normalized velocity. It will have a magnitude 1. So if we plot in this way, in a transformed vertical axis, if we plot the basis of the assumption of the boundary solution for the bound layer is that These three curves will converge into a single curve. So as far as the flat plate bound layer is concerned, we can express u by u infinity as a simple function of g of y by delta. So this is the starting point of the solution of the boundary layer by Blasius. So this is u by u infinity is equal to g of y by delta. And then he has used continuity equations to develop a string function. So not continuity equation. He has derived the stream function from the velocity u. He has developed a stream function, and from the stream function v is derived. So when you are deriving v from the stream function, the continuity equation will be automatically satisfied. So this, this is equal to, okay. This implies that u is equal to u infinity into g of, for the sake of clarity, this y by delta is denoted by a single a single Greek letter eta. This is eta. Eta is y by delta, so that we can write u is equal to u infinity into g of eta, and we know that u is equal to dou psi by dou y is equal to u infinity into g of eta, where eta is equal to y by delta, and delta we have earlier derived delta as is of the order of delta. We know that delta is of the order of, exactly not, but it is order of uh, nu x by u in nu x by u. So nu infinity by nu x by u infinity, so that eta is equal to y into square root of u infinity by nu x. This is what is eta, and now this equation can be integrated at a particular constant value of x, that is partially with respect to y, to get psi is equal to integral u infinity d of eta into dy, that is integration. So integral u infinity, since d is in terms of eta, we write d eta d eta multiplied by y. Eta is a function of y and x, so the Jacobian here is d dou y by dou eta, and that we can get from here. Dou eta by dou y is equal to square root of u infinity by nu x, and so dou y by dou eta is the inverse of that, nu x by u infinity. So we have this as u infinity d eta d eta into square root of nu x by u infinity, and this simplifies here one, here root is as for the entire thing will become u infinity nu x integral d eta d eta, and we assume that the integral g eta d eta is equal to some function of eta, so that we can write it as u infinity u x into f of eta as the expression for psi. Okay, that psi is actually psi is a function of xy, is like this. And if this is the case, if this is the case, integral of g eta is f. That way we can write as g of eta is df by, that is antiderivative is integral f dash is. So the psi is in terms of f theta. So we get it back g eta as u is equal to u infinity into G is f dash eta. So we write everything in terms of f. One is f eta, one is f dash eta. So we have the stream function as is a function of eta and velocity as a f dash eta, the derivative of f. So once we have this u, we can find out these terms of these momentum equation. So which requires v. First, let us find v. Once we have psi v is equal to minus dou psi by dou x. So this is x. Eta also contain x. So we have to do it as a product of two functions. So u infinity mu x and f dash eta into dou that is dou eta by dou x. So and plus next will be f theta f theta as constant square root of mu infinity mu and root x is 1 by 2 root x. And this further simplifies as mu infinity mu x f dash into dou eta by dou x. So eta is like this. Eta is like this. So we are having y then square root of mu infinity. There is a mu in there. X raised to minus 1 by 2 minus 1 by 2 x raised to minus 3 by 2 plus f root u infinity mu by 2 root x. And this x raised to minus 3 by 2 is denominator x raised to 3 by 2 which is an x in the square root of this can be replaced by x in the square root. Okay, so 1 root x one this root x and this root x goes. So there is uh, there is there is there is an x here which does root x and one x here, so that way that is also inside root, so that we have something like a minus 1 by 2. Okay, so we can take this first square root of u infinity u by by so within root there is an x and then is a 1 by 2 into there's an f here, there's a minus sign of this 1 by 2, this 1 by 2 is taken outside, this is taken outside, this is taken outside, then f dash y in the square root of u infinity by ux, this is eta, this is eta itself. So we obtain this kind of a form. So this is v. Now you are having this one, but my equation contains dou u by dou x also. So find out dou u by dou x also. So u is now u infinity in the f dash eta. Dou u by dou x is u infinity is constant. F double dash eta into dou eta by dou x. That is dou u by dou x. So it is equal to u infinity into f double dash eta into dou eta by dou x has a y in it. There is a u infinity. There is a mu is there. There is a root x is there. That becomes minus 1 by 2 x raised to minus 3 by 2. So that can be written as x into divided by x into root x, and that comes here. So minus 1 by 2x and u infinity into f double dash eta into this is eta, that way we can write. So dou u by dou x is obtained like this. Okay, now so dou u by dou y. So dou u by dou y is equal to This is u infinity is there. F double dash eta into dou eta by dou y. That becomes u infinity f double dash eta into dou eta by dou y is the y alone will come, will only go. So u infinity by mu x. So and dou squared u by dou y squared becomes one more derivative, so that is u infinity f double dash f triple dash eta in the square root of u infinity by mu x in the square root of u infinity by mu x. Now we have all the terms, this is there, this is there. So to do for this momentum equation, so u into dou u by dou x. So what is u is u is u infinity, u infinity, u is u infinity into dou u by dou x. U is u infinity into f dash eta, and dou u by dou x is here it is there, minus u infinity by 2x into f double dash eta into eta. So that is there. So this is the term. This is the term u into dou u by dou x. So for that we have this entire thing. Plus v into dou u by dou y. So for that v I have substitute. V is obtained here. We have obtained v over here. I copy this. Copy this. So v is here. V is here. So this v into dou u by dou y. Dou u by dou y is here like this. Dou u by dou y is here like this. So u infinity f double dash eta in the square root of u infinity by mu x, and this is equal to, so this is basically this is v into dou u by dou y, and the final term is this is equal to nu into dou squared u by dou y squared. So we have a new dou squared u by dou y squared is u infinity f triple dash eta into these two terms together, u infinity by mu x. So now this new cancels. So there is a u infinity here, u infinity squared here. So in this term there is a u infinity squared. Here there is a u infinity, under root u infinity, under u infinity, and this u infinity squared. And there is below there is an x is there. Let us see if that x is going. So this x is there, this x is there. So there's a root x here, there's a root x here. So these two goes. So there's a new here, there's a new here, that goes. So finally we have something like I will not put eta, but I'll put f dash. That feels f dash eta. So everything has gone, but the negative sign is there. Then there's a 1 by 2 is there. F double dash is there. F double dash is there. Then there's an eta is there. Then here also there is a minus 1 by 2 is there. So everything is gone. So f minus f dash eta, and here f double dash is there, is equal to right hand side f triple dash. So this is the form we have. So let me take it the next page and make as the final simplification. So this is minus f dash f double dash by 2 eta minus half f double dash, then half f dash eta f double dash is equal to f triple dash. And this term and this term are equal and opposite, both. So we get f triple dash plus half into f double dash is equal to 0, where f is a function of eta to be determined. So what is the advantage of this? This is actually d cube, d cube f by d eta cube. And this is f itself, this is d squared f by d eta squared. This is an ordinary differential equation in terms of f. So the similarity, this is why we got an ordinary differential equation that implies that the u by u infinity is exactly a function of eta. That means the variations of velocity are self-similar. The variation of velocity here are self-similar, that can be collapsed into a single curve by using a transformation variable called similarity variable. And that assumption or that hypothesis was true, because that is the reason why we obtained a ordinary differential equation for the f. So f is a function that is popularly called as the Blasius function, which has certain interesting mathematical properties like singularity, etc. So this function has certain singularity at some value of eta is equal to something like minus 1.56 or so, near to that. So there's a problem of expanding the function into a series beyond a certain value of eta. So if we are expanding about eta equal to 0, if we are expanding about eta equal to 0, we cannot expand that expansion will not be converging for eta greater than 5.6. So Blasius has solved this equation by using the boundary condition. What are the boundary condition is u by so what are the boundary conditions is u is equal to u at y is equal to 0 is equal to 0. U at y is equal to 0 is equal to 0. When y is equal to 0 implies eta is equal to y into square root of u by u x is also 0. So y equal to 0 implies eta is also equal to 0. So u by u infinity is f dash eta, right? So this gives u is equal to 0 implies f dash 0 is equal to 0. F dash 0 is equal to 0. And psi is equal to square root of u infinity nu x f of x. And the flat plate, bottom flat plate, that is y is equal to 0, is a streamline. It's a streamline. Flat plate is a streamline. The streamline are taking that psi is equal to 0 there. Psi is equal to 0 there. Sorry, this is not x but eta. So x is equal to 0 means eta is equal to 0. So y is equal to 0 means eta is equal to 0 and psi is equal to 0. That gives f0 is equal to 0. And we have at the edge of the bound layer at y is equal to delta is equal to delta u is equal to u infinity, and also that the velocity gradient becomes equal to 0. Dou u by dou y is equal to 0 at y is equal to delta. Y is equal to delta implies eta is equal to 1. Sorry, at larger distance. Okay, at larger distance, at any value of y at larger distance, not at y is equal to delta. Y at delta we have dou u by dou y would be becoming equal to 0, because not exactly at delta, because that is at 99% only the velocity is there. It will be somewhat will be having a certain value, but we can say that at eta is equal to infinity, very large y distances, that is eta is equal to infinity. The velocity gradient means f double dash of infinity is equal to 0. So these are the boundary conditions. So these are the boundary conditions that can be used to solve this. So the Blasius solution for the boundary condition, we have the equation f triple dash plus half of f double dash is equal to 0 subject to the condition that f 0 is equal to 0. F, f double dash is equal to 0. So these boundary conditions can be used and solve this. So this can be solved by this is solved actually. Blasius has solved this in a tedious manner by using a series expansion. Series expansion. We started with a series expansion about eta equal to 0, so that we write f eta is equal to some a0 plus a1 eta plus a2 eta square plus a3 eta cube plus a4 eta raised to 4 plus etc. And I will have a lecture on this showing how by taking a series expansion around about x by eta equal to 0 in solving this equation. This actually the complexity of this particular equation is f and the product f and f double dash is coming together, that makes this equation non-linear. So this is a non-linear ODE which need to be solved, and the series expansion solution I will be discussing in the next class, next lecture.